In the last couple of videos, we took a look at friction and how that dissipative force always opposed the motion of an object. And now we'll go ahead and take a look at its cousin, drag. Now with drag, the idea is, say you have some object that's just moving through a fluid. So I will mark this region out here as being a fluid. And to a physicist, a fluid is any gas, liquid, or plasma. And certainly this will work here. So, but we can just think air. That'll be fine for what I'm going to focus on here. So as we go through the fluid, what's going to happen is individual atoms and molecules in the air are just plain going to collide off against the object, like that, say, or that one collides like that. And in so doing, they're literally pushing on the object to oppose the motion. So we'll say that's the velocity. And so as a result, the object will feel a combined force from zillions of atoms that seeks to oppose the motion. So it'll always be anti-parallel to the velocity. So you can say here it always opposes the motion. Which means that the drag is anti-parallel to the velocity. So far, so good. This is reminiscent of friction for us. The difference is the how we model the magnitude of drag. And to be fair, the analysis of drag gets really gnarly really fast. To do a full detailed treatment, you have to worry about things called Reynolds numbers, and in certain cases, even that isn't good enough. And you just have to plain full on do a computer numerical simulation of blocks of groups of atoms colliding off against the object in order to get any kind of meaningful analysis. That's a field called computational fluid dynamics. And it gets super hairy super fast. Even in the regions where you can write a more typical, or at least an equation for it, depending on the regime, you might either write an equation where the drag is linear, the magnitude of the drag is linear to the object's velocity, or where it's quadratic to the object's velocity. So I'm just going to do the model where it's quadratic. So this is a model of drag, but not the only model of drag. So in this model of drag here, and this is applicable for most kind of real world scenarios, like looking at a skydiver or something like that, the drag is equal to 1/2 CD. I'll explain these symbols in a second here. So this C sub D is a quantity called the coefficient of drag. And it depends on both the fluid and the roughness of the object moving through the fluid. This thing that looks like a funny P, it isn't actually a P. It is a lowercase Greek letter rho. The way you draw rho is you start down here, you go up like that, and you resist with all your might the urge to turn it into a tadpole. Sorry about that. There we go. So that's how you draw a rho. That's one variant. Other people like to draw it like that. Again, resist the urge to turn it into a tadpole. All right, but either way you'd like to draw it, what this Greek letter rho stands for is the density of the fluid. I'll just say of air here because that's all I'm really going to focus on in this presentation. Units for that are kilograms per cubic meter. The coefficient of drag has no units. this A here is called the cross-sectional area. So so the units of that are going to be square meters. So what we can imagine the cross-sectional area is think like if you were to have a light source far away from the object, and it was directly in front or directly behind the object as it was moving, and you were to look at shadow, it would be the area of that shadow. So for instance here, with this ball that I have going through the air, the cross-sectional area would be the area of this circle here at its fattest part. Okay. Oops, sorry about that. Now, for a typical skydiver type of situation, so I'll just say for a skydiver-like thing, and this won't be exactly right because it depends on the clothing the skydiver's wearing and stuff like that. So I'll put that in quotes. We can take this 1/2, the coefficient of drag and the density of air, and turn this all into a number that's roughly 1/4 of a kilogram per cubic meter. And then we still times it by the cross-sectional area of the skydiver, which is probably going to be the skydiver's parachute, to be honest, times the square of the speed. All right. So let's go and take a look at our intrepid skydiver here. So at first, let's just say our skydiver is falling down feet first because they're just about to launch the parachute. They're heading down like so. In this case here, they're going to be moving pretty quick. And the reason for this is that their cross-sectional area is only the width of their body. It is basically the shadow of their body if the sun were right directly above them. So it's not very big. So comparatively speaking, the force of drag might not be all that big if this is still reasonably soon after they jumped out of a perfectly good airplane. And we would have the force of gravity down, and so we could imagine the skydiver starting to pick up speed. Then we could imagine that they open up their parachute. By opening up their parachute, what they've done is they've effectively made their cross-sectional area a whole lot bigger. And in so doing, they'll make the drag force a lot bigger. And depending on how fast they're going, it's entirely possible that the force of drag could even exceed the force of gravity on the skydiver. And so you could have a situation, say, where the skydiver is accelerating upward. Well, either way, either we're going to accelerate downward, and if we accelerate downward, we'll pick up speed. But as we pick up speed, the drag force will increase, which will decrease the amount of acceleration, but you'll still be picking up speed, just more slowly. And what that means is you'll eventually approach a speed where the force of gravity and the force of drag are the same. Or in the case here where the skydiver suddenly opens the parachute and they were already going too fast, the force of drag could be bigger, which means they're accelerating up, which means their speed would decrease. And their speed would decrease less and less violently as the force of drag matches the force of gravity. So this situation where the two are equal, where the two forces are equal, gets called the terminal velocity. And again, this is one of those cases where it should really be called terminal speed, but nobody does. And so this is the situation where the drag force and the force of gravity are equal to each other, which will give us an acceleration of 0. All right, so we can calculate what that speed is. by setting the force of drag equal to the force of gravity. So 1/2 CD rho AV squared will equal mg. And so in this speed here is our terminal speed or terminal velocity. So solving for that, V terminal will equal the square root of 2 mg over CD rho A. All right, so this is, again, only for the regime where quadratic drag is valid, but most skydiver type situations are in that regime. So what do we see from this? Well, the bigger the object's mass for the same cross-sectional area, so the denser the object effectively, the faster it'll fall through the air. So this is why, for instance, if you wad up a piece of paper down to the size of say a steel, down to the size of a marble, and you drop it and a marble at the same time, you'll see that the marble will hit the floor first, and this is just because the wadded up piece of paper will be more rapidly approaching its lower terminal velocity than the marble. And as we already mentioned, the smaller the cross-sectional area, the faster you'll go down as well. Also depends on what you're falling through and all of that, but those are the biggies. Now, to do a detailed analysis of this involves solving differential equations, and they can sometimes, and this is one case where it can be solved symbolically, but most of the time with these kind of calculations, you end up doing them numerically. And so I thought I'd just give one particular example here. So I wrote some numerical solution code in a specialized programming language called Mathematica. And I'm imagining that our skydiver is presenting 2 square meters of area. They're on Earth, and that our skydiver has a mass of 75 kilograms. And because I had to have an initial height, I assumed that they were far enough above the Earth that I didn't have to worry about it, so I put them at 1,500 meters above the Earth. I used our skydiver version of this, of the drag equation here with the 0.25 already built in. So this is Newton. This doesn't look like it, but this much right here is Newton's second law. This is and this is y double prime, so this is the second derivative of y with respect to t, so this is ma equals minus mg. I already put the model for gravity in directly, plus our drag force, and the reason for the plus sign is because since our skydiver is falling down, minus sign, the force of drag opposes that motion going up, plus sign. And I went ahead and numerically solved it for the case where the skydiver was already heading downward at 20 meters per second. So what we can see is that at a little more than that our skydiver approaches a terminal speed of, in this case, a little more than 38 meters per second, about 38 and a quarter. So this is a plot of the velocity as a function of time here. Here is a plot of the acceleration as a function of time. And so we can see that the skydiver is accelerating downward, picking up speed. However, the rate at which the skydiver is picking up speed is decreasing, and the acceleration asymptotically approaches 0 as the skydiver's speed asymptotically approaches the terminal velocity of about 38 and a quarter or so meters per second downward. Now let's say our skydiver was already falling faster than that. Let's say they're going at 50 meters per second downward, and want to see what would happen there. So this would be faster than the skydiver's terminal velocity. Okay, so what we see happen here is the skydiver is slowing down to the terminal velocity. So you can either, if you're going slower than the terminal velocity, you'll pick up speed to it. If you're going faster than the terminal velocity, you'll slow down to approach it. So here our skydiver is falling down at 50 meters per second. That decreases down to eventually approaching our same 38.25-ish meters per second. And we can see here now that our acceleration is positive. This means that the acceleration of our skydiver is pointing up, even though our skydiver is falling down. And again, we can see that the acceleration is asymptotically approaching zero as our skydiver's speed approaches the terminal velocity. Alrighty, in the next video, I'm going to kind of turn tack for just a moment and take a look at situations with strings going over pulleys and stuff like that. So I will catch you in the next video.